In this video, I want to talk about some things we talked about previously having to do with association and describing bivariate data. And then I want to start talking about correlation, how we can actually put some numbers to some of these ideas. So first of all, just an introduction. Suppose a study finds a high positive association relating family income to SAT scores. Which is the explanatory variable? Well, the explanatory variable here would be the family income, that we think that is explaining the SAT score. Okay, so I'm just going to put the E and the R in there. What is the proper conclusion? That poverty causes low SAT scores, that wealth causes high SAT scores, or that there's a strong association? It is this last one. This is the only proper conclusion here. A graph looking good, something looking linear, does not mean the explanatory causes the response. And remember the kind of silly graph I showed you about shoe size and reading. Having larger feet does not cause you to be a better reader. Okay, so all we can say is that there's a strong association there. We can't say anything about cause and effect. Okay, here's some data I collected from one of my classes on the number of aunts and uncles they had and the number of cousins they had. And I made a graph here of that data. Okay, so if you could think about maybe drawing a line through this, you know, something like this. Let's just think about and talk over our description of this. So direction, it's positive. There's a positive direction here. I'll come back to outliers. Form, I think a linear equation would fit this best. And strength, I think it's fairly strong. I think the data fits pretty well along that line. In terms of outliers, I think the only one that might be an outlier, maybe this one. You know, maybe you could make a case that is an outlier. Everything else seems really close to the line. So, and just a quick point to the fact that this person right here with the 29 aunts and uncles and 35 cousins, they fit the trend. So even though they're far away from the other data, they aren't an outlier. An outlier, remember, is no longer just is it far away from the other pieces of data. Now it's all about is it far away from the trend that has been set. Okay, so I think, again, this yellow one, I even think that if this is an outlier, it's really not an outlier by much. So you maybe even would say none. Okay, now, what we've done here in describing the strength is very general. So now I want to start talking about how we could be more specific and put a number to this. Okay, so association, what we've talked about with positive association, negative association, just kind of those trends, those are very general. Now we're going to put some numbers to it. We call that correlation. Correlation is quantitative. It will return a number. Now there are a number of ways to think about correlation. You can see kind of this is the way I used to tell students how to remember it, is that for the explanatory and response variable, we calculate their z statistic, so this is for Zorro, the z statistic for each one separately. Okay, so you would find the average explanatory and sample deviation for it. You'd find the average response and deviation for it, and then you would take each ordered pair and calculate the explanatory z and responses z, and then you would multiply them. So you would condense this ordered pair down to one number using a product. Then you would add all of those products up and divide by essentially n, but in this case, similar to the sample deviation, I put n minus 1 here. That formula uses n minus 1 to create a little more room for error. But essentially, what this calculates is the average z statistic product. Okay, that's kind of maybe the most difficult way to think about this, but the most used formula. Another way to think about the formula that if you think about having a plot, and let's put a couple of points out there, and I'm just going to keep it at 2, even though obviously you know this would make a line. If you think about having 2 data points, and Obviously, this is oversimplified. We should have more, but I think you'll get the idea here. If we drew a vector to each of those, and then we calculated the angle between the vectors, this is another way to think about correlation. And if you think about if all of the points lie along the same line, the angle between them is 0, and the cosine of 0 is 1. 1 represents a correlation where every point is on a line together. On the other hand, if the angle between them forms 90 degrees, all of these angles form 90, the cosine of 90 is 0. A correlation of 0 means the points are not at all correlated because their vectors pull in opposite directions. Okay, so this is kind of a multivariable way to think about the correlation formula. It actually would return the same formula. Yet another way to think about this is, if I could really quick just put some points here like this. Correlation has to do with an ellipse being drawn around the points. So if I can draw an ellipse around all of the data points like that, and I missed one, the skinnier the ellipse, the closer the correlation is to 1. And the bigger the ellipse, meaning circular, the closer the correlation is to 0. Okay? All of these ideas lead to the same formula if you simplify them, but it's just a couple of ways to think about correlation. Okay? Again, correlation is a number that relates to how linear data is, how strong that linear relationship is. And a positive correlation means we had a positive association. A negative correlation means we had a negative association. So correlation will always lie between 1 and -1. 1 being a perfect correlation in the positive with a positive slope, or all the data is along a line with a positive slope, and a correlation of -1 means all of the data is on a line with a negative slope. So let's look at some websites that illustrate this. Okay, so in this first video, or this first website that you see, the correlation here is 0. Okay, and you can see kind of the smattering of points. Think about what I said about the circle that you would, or the ellipse that you could draw around. It would look very circular. And as I drag this, I'm going to start moving this towards like 0.5. You'll see the point slide. So now we're getting a little skinnier ellipse. It's getting closer and closer to linear. And of course, the higher you go, the more those points are going to look linear. If I go all the way to 1, they're all on the same line. Okay, so there's like 0.82. You can see how linear that is. And then going negative, see how that correlation would look. Okay. Okay, in this one, I can draw some points. And you can see the correlation up here. So right now the points look pretty linear. If I continue to do that, okay, you can see a very high correlation. I just really wanted to show what happens when I add an outlier to that correlation. See how much it changed? So not resistant to outliers for sure. Look at this. Now it's 0. I add one more. Now it's negative. So all of that positive trend is just thrown by those 3 points. We talked about influential points the other day. Take a look at this little, I'll try and draw a little square. See, correlation's really close to 0. Now I'll put a point up here. And now it's almost 1. So again, this talk of influential points and how they can really dictate our correlation. So to close this video, the big things to know about correlation are that it is quantitative, that it takes values between -1 and 1, that it describes the strength of a linear relationship. And all of the ways we talked about the calculation of this are cumbersome. So in the next video, I'm going to show you on your calculator how you can calculate this really quickly, and we'll kind of close up our correlation discussion.